Our lesson for today is all about stack and subroutines. Stack is a group of memory locations. Those locations are related to write memory and read memory. It is used for storage of binary information during the execution of the program. Stack also follows LIFO or last in last out. It is only used for storing and retrieving data but not for data storage. The three stack instructions. First is the LXI-SP. This instruction will define the beginning of the stack. So by getting this instruction you are going to initiate your stack pointer. It is used to create and initialize the stack pointer sequence. For example, we're going to have LXI-SP 16-bit address. It will create a stack pointer with your 16-bit address. Whatever 16-bit address you are providing, that can be stored in the stack pointer. So now coming to the second instruction, this is push RP, where RP stands for register pair. We have many register pair in microprocessor, which are BC, CD, HL. All these are register pair. Each are having 8 bits each and the pair is 16 bits. This instruction copies the contents of register pair to the stack. So now, for every push operation you need to decrement the stack pointer first, and then you need to push or copy the content to their register pair. So now, for example, I'm taking this program LXI-SP-FFFF. That means it will initiate a stack pointer with address FFFF. And coming to push B instruction, before pushing B you need to decrement the stack pointer, because push RP is a pre-decrement operation. That means if you're going to push anything, you need to decrement your stack pointer first. So here, after decrementing the first stack pointer, it will give you FFFE. Into this location you need to store the contents of register pair B. So the contents of B is BC is equal to 10A2H. Then the contents of B is equal to AF12H. These are the contents of both register pair B and D. What we're doing now is pushing B. That means you're copying the contents of this register pair to the decremented stack pointer. So now, you need to copy the higher order address of BC's register pair. The first higher order address of BC is 10. This 10 will be copied to the FFFE stack pointer. Now, we need to push the lower order address. Again, to push your lower order address, you need to decrement your stack pointer. So that means to FFFD. So now I'm copying A2. So this push B operation is now complete. After push B instruction we're moving on to the push D instruction. Again, you need to copy the higher order address of this register pair. The first higher order address of D is AF. This AF will be copied to the FFFC stack pointer. Now, we need to push the lower order address. Again, to push your lower order address, you need to decrement your stack pointer. So that means to FFFB. So now I'm copying 12. So this push C operation is now complete. Executing this instruction LXI-SP, FFFF, the stack pointer is initiated with the initial address or maximum address FFFF. So this can be done by first instruction. And these two can be done by your second instruction. Also these two can be done by your second instruction. Coming to pop operation, this is reverse to push RP. In push RP we copy contents to stack, while on pop RP we retrieve contents from stack. It is used for retrieving the elements stored in stack. For every pop, get 1 byte from stack to lower register pair and increment the stack pointer. Then, get another 1 byte from stack to higher register pair and increment the stack pointer. For example, we have stack and we're executing pop H operation. We are having register pair HL. In L we can store the lower order address, and in H we can store the higher order address. We need get 1 byte. 1 byte is equal to 8 bits. That means 3F will be copied to the lower order address. And pop H operation is not yet completed because we didn't retrieve the higher order address. Before popping 3F, you need to increment your stack pointer. It means you need to add 1. From FFF11 it will become FF12. That means the stack pointer is now pointed to FF12. After that you will copy 32 to the higher order address. So same like in POP PSW, it is the combination of accumulator and flag register. Is nothing but as a small program that can be called whenever we require. Subroutines can be written and stored separately, so that whenever we require, we just call the subroutine and after that we will just return it to the main program. The block of instruction which carries out a specific well-defined task is called a subroutine. Subroutine halts the main program where the execution of instruction and sequence happens. It provides returning to the same point it transfer control to subroutine it execute the subroutine then revert to the main routine. Whenever call occurs it go back to the subroutine program. When subroutine sees the return statement it will go back to the main program. Then more program will be executed. Then call occurs again then it goes again to the subroutine and goes back to the main program. Instruction move operands and perform arithmetic operations such as addition and subtraction. The operands involved in these instructions have fixed length of 32, 16, or 8 bits. To illustrate the use of logical instructions, let us consider this example. Suppose that the register D1 contains some 32-bit binary pattern and we want to determine if the pattern in bit positions B18 through B14 is 11,001. And .L hashtag S700 D1 CMPLL hashtag S6400 D1 BEQ. Yes, the first instruction performs the logical and of individual bits of the source and destination operand, leaving the result in D1. The hex number 7C000 has 1's bit positions through B14 and 0's elsewhere. Thus, as a result of the AND operation, the 5 bits in position B18 through B14 in register D1 retain their original values and the remaining bits are cleared to 0. The subsequent compare instruction tests whether these 5 bits correspond